Welcome back to The Deep Dive, the show where we take the most fascinating new research, peel back its layers, and really try to extract the truly insightful nuggets of knowledge and insight just for you.
It's great to be diving in again.
Today we're embarking on, well, one of the most audacious, enduring quests in all of science, the search for a theory of everything.
Absolutely. For centuries, some of the most brilliant minds humanity has ever produced have really wrestled with this monumental challenge.
Yeah, how do you truly unify quantum mechanics, which describes that bizarre, probabilistic world of the very small with general relativity, our magnificent framework for understanding gravity in the universe on its grandest scales?
And it doesn't stop there, does it? You also have to weave in the fundamental forces that sculpt our reality.
Exactly. Electromagnetism and the strong and weak nuclear forces. It's often been called the ultimate riddle in physics, a grand, unfinished symphony.
A symphony that's been missing its unifying theme, perhaps.
Precisely. Well, today we're plunging into a piece of research that dares to propose a radical, maybe even elegant answer. Our deep dive centers on Philip Lillian's groundbreaking paper, Coherence Eigenstates, Fractal Calculus and Gauge Emergence.
And this isn't just, another incremental step. Some are framing it as a breakthrough of the highest order, a Tier 4 Eureka breakthrough, as Lillian puts it.
Suggesting a potentially revolutionary new way to understand the very fabric of reality itself.
What's truly at the heart of Lillian's framework and what makes it so compelling is what he terms the coherence first ontology.
Coherence first. Okay, what does that mean exactly?
It's a profound conceptual shift. So instead of beginning with particles as the fundamental building blocks, or even say fields as the primary entities.
Which is how we usually think about it, right?
Pretty much, yeah. Lillian proposes that the entire intricate structure of reality, from the forces we experience every day to the fields that permeate space, and even the discrete particles we detect, doesn't arise from arbitrary, sort of predefined rules.
Okay, so where does it come from?
It emerges directly, organically, from the geometry of coherent resonance pathways within a deeply complex, multi-layered space.
Wow. Okay, coherent resonance pathways. So, reality isn't Lego bricks.
Exactly. Imagine it more like a vast, interconnected symphony. The coherence is the underlying harmony, the resonant patterns. And from that harmony, all the individual notes, the particles, the forces, the dimensions, naturally crystallize and emerge.
So it challenges our deep-seated intuition of discrete things and suggests this continuous, interconnected fabric.
Precisely. A fabric from which everything we observe ultimately takes shape. It's not just a different starting point, it's really a redefinition of what fundamental even means in physics.
So our mission today is to take you on a journey into this concept. It's certainly going to stretch our minds a bit, no doubt.
It's definitely a mind bender, yeah.
But by the end, you'll hopefully have a much clearer grasp of what this coherence-first idea means, how it's mathematically constructed, and crucially, how it translates into the observable physics of our universe.
We'll be diving deep into the intricate mathematical heart of this breakthrough, really focusing on how these abstract concepts, these coherence eigenstates, could actually give rise to the very universe we see and interact with every single day.
Let's unpack this fascinating proposal then.
Indeed. And I think to fully appreciate the sheer audacity and magnitude of Lillian's work, we first need to understand the persistent, grand challenge that has truly vexed theoretical physics for decades.
Right. The context is key. As you mentioned, the core problem is the struggle to reconcile those two towering achievements of 20th century physics.
Exactly. On one hand, quantum mechanics, incredibly successful theory, describing the world of the very small subatomic particles, their strange, probabilistic behaviors, their interactions. It predicts experimental results with just astonishing precision.
Mind-bogglingly accurate. And on the other hand,
General relativity, Albert Einstein's masterpiece, masterfully describing gravity and the universe on its largest scales, from planets orbiting stars to the evolution of entire galaxies, the cosmos itself.
two pillars, incredibly successful on their own turf, but fundamentally incompatible in many ways.
That's the core issue. And beyond reconciling those two, there's that ongoing effort to integrate the fundamental forces.
Right. Electromagnetism governing light, electricity, magnetism, responsible for, well, almost everything chemical and technological.
Then the strong nuclear force, binding atomic nuclei together, essentially holding matter itself in existence.
And the weak nuclear force responsible for radioactive decay, nuclear fusion in stars. Crucial stuff.
So the big question remains, Why is it so incredibly hard to bring these vastly different scales and forces under one elegant, unified roof? What's the fundamental roadblock?
That's the crux of it. Conventional frameworks, while powerful individually, often run into profound conceptual and mathematical roadblocks when they attempt this unification.
And Lillian offers a very sharp critique of these existing approaches, highlighting where he believes they fall short.
Okay, where does he start?
For instance, he points out significant limitations in what he refers to as Riemannian models. These are the traditional geometric frameworks, like those famously used in general relativity.
Which describes space as fundamentally smooth and isotropic, right?
Exactly. Isotropic means the distance or path between 2 points, and the effort it takes to traverse that path is the same regardless of the direction you're traveling, uniform in all directions, like moving across a perfectly smooth, unblemished billiard table.
I see. So Lillian is saying that this smooth, uniform assumption about space is actually a fundamental limitation. It's too simple.
Precisely. He argues that these conventional models cannot encode anisotropic directional coherence or self-similar fractality.
Okay, let's break that down. Anisotropic directional coherence.
It means that the way information, energy, or fundamental patterns, what Lillian calls coherence flow, isn't uniform. It's inherently directional.
Like navigating a dense forest.
That's a great analogy. Some paths are clear, easy to traverse, while others are incredibly difficult or even impassable, depending on which way you're trying to move. The geometry of the forest isn't isotropic, it's highly directional.
And self-similar fractality, like coastlines.
Exactly. Patterns that repeat themselves at different scales, branching trees, jagged coastlines. You see similar structures whether you zoom in or out. Traditional smooth geometry just cannot capture this kind of intricate directional flow or the infinitely repeating, non-smooth patterns characteristic of fractals.
So Lillian's point is, if reality is inherently directional and fractal, then our geometric models must reflect that. We need bad maps.
We need maps that match the territory, yes. He also turns his critical eye to string theory.
Which, for decades, has been a leading contender in the unification game, right?
It has. But Lillian argues it relies on predefined dimensional counts and compactification rather than emergent dimensionality.
The extra dimensions problem. String theory often starts with, what, 10 or 11 dimensions?
Correct. And then it proposes that the extra dimensions are curled up or compactified into incredibly tiny spaces we can't observe. So the dimensions are essentially imposed from the outset. It's an assumption beered in.
Which highlights a key philosophical difference, doesn't it? Imposing dimensions versus having them naturally arise.
Precisely. Lillian's approach posits that dimensionality itself should naturally arise or emerge from fundamental principles, rather than being an initial assumption. Are dimensions input or output? That's the question.
A deep question. And what about quantum field theory, QFT, the basis of the standard model?
Hugely successful, yes. But Lillian critiques QFT for treating gauge fields as imposed mathematical structures, not emergent resonance phenomena.
Explain that a bit more. Gauge fields are the force carriers, like photons.
Yes. In QFT, these gauge fields are essentially added into the theory by hand to preserve certain symmetries. Those symmetries are put in by design because we observe them.
So they're rules we impose on the theory to make it work.
In a sense, yes. Lillian's coherence first view flips this. It suggests these fields and the symmetries governing them should naturally emerge from the underlying coherence dynamics. They shouldn't be built in as initial assumptions. The universe's rules of interaction aren't just given, they manifest.
So if those are what we might call top-down approaches, starting with particles, forces, imposed dimensions, trying to unify them,
Then Lillian's alternative is a truly bottom-up approach. He starts with this incredibly fundamental concept of coherence.
and sees how everything else, particles, forces, dimensions, even space-time itself, naturally grows, unfolds, emerges from it.
Exactly. It's like planting a tiny, almost invisible seed and watching an incredibly complex tree sprout, complete with its branching patterns, leaves, roots, all arising from the inherent logic within that seed.
Rather than trying to assemble a tree from pre-cut lumber and nails.
Precisely put, the seed, in Lillian's framework, isn't just a metaphor for a starting point. It embodies the inherent information and potential within coherence itself.
Like the acorn containing the blueprint for the oak.
Exactly. Lillian posits that the fundamental patterns of coherence contain the blueprint for all particles, forces, and even the dimensions we observe. It's a universe that doesn't just exist, it unfolds from its own intrinsic logic.
So what did he specifically set out to achieve in this paper? What were his stated goals?
He laid out some very specific, ambitious goals that will guide our deep dive. First, demonstrate how fractional derivatives map onto dimensional unfolding.
Okay, linking a specific math tool to dimensions appearing.
Second, show how eigenvalue spectra correspond to stable coherence attractors. Basically, how stable quantized patterns of coherence can be mathematically identified and predict states of reality.
Quantized patterns.
Okay. A third, and this is central, illustrate how gauge symmetries emerge as curvature phase solutions rather than imposed constructs. This is a revolutionary claim.
The emergence of forces, right?
And finally, suggest how FCHP predicts observable coherence effects in high-energy and cosmological regimes, hinting at concrete ways we might actually test this revolutionary idea experimentally.
Ambitious goals indeed. Let's see how he tries to tackle them. Okay, so we've set the stage, we understand the immense problem Lillian is tackling, and we know his ambitious goals. Now, let's dive into the extraordinary canvas upon which this new reality is painted. The Finsler Coherence Hyperfractal Phase Space, or FCHP. What exactly is FCHP?
Right. FCHP is introduced as a higher dimensional manifold where coherence is geometrically encoded, integrating Finsler anisotropy with hyperfractal dimensional layering.
Okay, that's a dense phrase. Let's unpack it. It's not just a mathematical space.
No, and this is the profound conceptual shift. Lillian posits that the geometry of coherence defines the structure of reality itself. It's not just a blackboard where physics happens.
It is the structure, the foundation.
Exactly. It's the actual foundational space from which everything we observe, forces, fields, particles, fundamentally arises. It's like saying the notes and instruments of the symphony don't just play in a space. The very space they play in is the unfolding resonant patterns of the music itself.
Wow. So it's not just a space where physics happens, it's the space from which physics emerges. A huge distinction.
Ontological, really.
And within this FCHP, he uses something called the Finsler metric. How is that different from, say, the Riemannian metric used in general relativity?
The Finsler metric is absolutely key, essential for encoding this directional coherence we talked about.
Because Riemannian models or isotropic direction doesn't matter locally.
Exactly. Think of the surface of a sphere moving north as locally the same as moving east. But FCHP is fundamentally different. It uses a Finsler metric, and this is where the anisotropy, the directionality, comes in.
How does it work, mathematically? Briefly.
Well, mathematically, a Finsler structure, $5, is a function $5 from the tangent bundle, TM dollars, to the positive real numbers, $5 TM right RO math Baylor, plus
Tangent bundle.
That involves directions, right? Yes. Conceptually, it means the length or effort of a path isn't just determined by your position, second or coordinates, but also by your instantaneous direction components within that space. It takes both the 0.6 oz and the direction you're moving in at that point.
So it's not just where you are, but where you're going from that specific point that defines the metric, the very fabric of the space. That feels intuitively different.
It is. And the Finsler metric tensor, which formally defines the distance or interval, is given by seceston f's y f2 partially partially off.
Okay, let's focus on the meaning there. The key is that seceston depends on both $6 and Euler, position and direction.
Exactly. That explicit dependence on both position $6 and direction Euler's was absolutely critical. It allows the metric itself to encode anisotropic coherence.
So the geometry has a memory or a preference for certain directions. It's not a uniform medium, it has a grain.
Precisely. And this is fundamental because coherence gradients in SCHP are inherently directional. So think about navigating a complex landscape again, maybe a vast ocean with strong currents. The effort required to move isn't just about distance. It profoundly depends on the specific current you're swimming against or with, the direction you're facing. Some paths might be incredibly smooth, require less coherence energy if you move along a certain orientation, aligning with the flow.
While others could be really tough, going against the grain.
Exactly. Rugged, energetically demanding. This unique characteristic allows the geometry itself to remember and represent the directional flow and resistance of this fundamental coherence. It's a radically different way of thinking about the fabric of space.
And it's not just directional. The name says hyperfractal. What does hyperfractal dimensional layering mean? This sounds way beyond 3 or 4 dimensions.
It is incredibly dynamic. Hyperfractal layering means FCHP is not a smooth space with a fixed static number of dimensions. It's not just 3 plus 1 or 10 or 11.
So what is it?
It incorporates this idea of hyperfractal dimensional emergence. This is where new effective dimensions arise from fractional derivative orders along the FCHP manifold.
Okay, wait, new dimensions arise. How?
Think of a familiar fractal, like that coastline or Romanesco broccoli. As you zoom in, you discover more intricate detail, more convolutions. It's like revealing more dimension at finer scales.
Right. The measured length depends on your ruler size.
Kind of like that, but more profound. FCHP takes this concept to a higher level, where these layers actively unfold, and new effective dimensions can literally appear or disappear depending on the underlying coherence dynamics.
So dimensionality isn't a fixed background, it's dynamic.
It's an emergent dynamic property of the coherence patterns themselves. The universe isn't simply in a fixed number of dimensions. Its dimensionality is a consequence of its own coherence. That's the claim.
That's a huge conceptual leap. Okay, so if reality's canvas is this weird directional, dimensionally unfolding FCHP, how do you even begin to describe dynamics on it? Like movement, change. Traditional calculus, with its nice, smooth derivatives, feels completely inadequate.
You're absolutely right. It would be like trying to describe wild ocean currents using a map designed for a calm, straight river. Traditional calculus relies on infinitesimal changes in smooth spaces, and FCHP is anything but smooth and static.
So what's the solution?
This is precisely where Lillian introduces what he calls fractal calculus. It's a generalized calculus, and its core mathematical tool, its innovation, is the pervasive use of fractional derivatives.
Okay, fractional derivatives. Not just first derivatives, velocity, or second derivatives, acceleration, but derivatives of like order 1.5 or
Leap,
0.7.
Exactly. Derivatives of a non-integer order, alpha.
What does that even look like mathematically, and what does it mean intuitively? How can you have half a derivative?
There's a fascinating and powerful extension. The fractional derivative operator, as defined by Lillian, looks like this. Math, gamma 1 alpha, franc 1, partial, gamma 1 alpha.
Okay, whoa, let's unpack that slowly. Partial y is the coherence function again.
Yes, describing the coherent state at $0.6 and direction mi is the fractional derivative operator with respect to the ith coordinate.
And that integral with the gamma function, that's the core of the generalization.
Pretty much. The integral and the gamma function are sophisticated mathematical tools that generalize the concept of a derivative beyond integer orders. The familiar partial x from classical calculus, is just a specific case when alpha happens to be 1.
So this alpha, the fractional order, seems critical. It's popping up everywhere. What's its significance?
That's absolutely crucial. You can think of it as one of the theory's central dials. Lillian states that varying alpha effectively probes hidden hyperfractal layers.
Probes hidden layers, like a zoom function.
Exactly, like a zoom function or a tuning knob. By changing alpha, you're tuning into different depths or scales of reality within the FCHP. Think about it. Traditional derivatives look only at the immediate local slope.
Right, the instantaneous rate of change.
But in a fractal space, the past, the history of the function, can profoundly influence its present behavior, like how the entire complex history of a coastline determines its current ruggedness. That integral, involving the path from 0 to $6, effectively allows the derivative to remember or integrate information from across a wider range, not just an infinitesimal point.
It gives the derivative a kind of memory, a non-local influence.
Precisely. Which is crucial for how coherence propagates through a space that is inherently non-smooth and multi-layered. It captures that fractal nature.
Does this new calculus connect back to what we already know? Can it reproduce standard physics?
Yes, and that's incredibly important for any new theory. If you set alpha to nullers, something remarkable happens. As alpha right RO, we recover classical smooth Finsler geometry.
Ah, so it contains the old framework as a special case. That's reassuring.
It shows it's a true generalization, not just something completely different. It subsumes known physics.
But the really radical part is when alpha isn't 1, right? What happens when it goes towards 0?
That's where the dimensional unfolding comes in. And it's a profound conceptual leap. As alpha right arrow dollar, Lillian states, new effective fractional dimensions unfold dynamically.
Meaning the number of dimensions isn't fixed. It can change based on alpha, based on the coherence dynamics.
Exactly. The space isn't fixed at 3 plus 1 dimensions, or any integer number. New effective dimensions can actively appear or disappear depending on the specific coherence dynamics being probed by alpha.
So what's the conceptual interpretation? How does this tie back to coherence?
The interpretation is groundbreaking. The fractional derivative governs resonance transfer across coherence layers, where alpha indexes how coherence projects into emergent dimensions.
Wow. So the math tool, the fractional derivative, directly controls how coherence moves between these fractal layers and how dimensions themselves emerge.
Yes. It links the mathematical tool directly and elegantly to the core coherence-first ontology. It suggests that the dimensionality we perceive isn't fundamental, but a manifestation of the underlying coherence's behavior across these fractal layers, tuned by this parameter alpha.
Okay, this is where it gets absolutely captivating. We have this exotic FCH piece, space dynamic, directional, dimensionally unfolding. We have the fractal calculus with its fractional derivatives to describe dynamics within it. Now, the million-dollar question. How does Lillian use these powerful abstract tools to derive coherence eigenstates and ultimately show how the fundamental forces we observe actually emerge? What's the central equation, the mathematical heart?
Right. The core of the math, the breakthrough that ties everything together, lies in what Lillian calls the generalized coherence field equation. This is the unifying equation. Left box alpha plus lambda alpha, right? Lambda alpha.
Okay, let's break that down piece by piece. It looks like an eigenvalue equation, maybe similar in form to the Schrödinger equation in quantum mechanics.
That's a very good analogy. It is an eigenfunction equation, but generalized for this profoundly different space. Let's look at the terms.
What's box alpha? Looks like a wave operator, the D'Alembertian, but with F for Finsler and alpha for fractional.
Exactly. Box alpha is the fractional Finsler-D'Alembertian. The D'Alembertian is the natural wave operator, describing how waves propagate. Here, it's generalized for FCHP. This term encodes coherence propagation within the FCHP.
So it tells us how these fundamental patterns of coherence, these waves of reality, move and evolve through this weird space.
Precisely. And the alpha superscript means this propagation itself depends on the fractional order. How coherence propagates can vary depending on which hyperfractal layer, which depth of reality you're observing via alpha. It's a dynamic wave equation for reality's fabric.
Okay. And what about MathCal alpha? That looks like a curvature term, R for Ricci maybe, but again with alpha.
It is. MathCal alpha is the fractional Finsler curvature scalar. This term is absolutely crucial. It describes coherence folding, gun folding along hyperfractal layers.
So not just how coherence moves, but how the space itself bends and warps in response to coherence.
Exactly. In traditional GR, curvature tells us how space-time is bent by massurgy. Here, the curvature FCHP isn't just a passive background. It's directly linked to how coherence patterns are folding, unfolding, organizing themselves across these multi-layered fractal dimensions.
So the geometry influences coherence, and coherence influences the geometry. It's an active, dynamic relationship.
Yes. It's like the universe's own self-sculpting mechanism. Coherence dictates the shape of its container, and vice versa.
Okay, so the left side describes coherence propagation and the space's curvature response. What about the right side, lambda alpha?
Right. Lambda here is the coherence eigenfunction. Just like eigenfunctions in quantum mechanics describe stable, allowed states like electron orbitals around an atom, each with a specific energy.
Here, it represents the stable patterns or waves of coherence that can exist within FCHP, the preferred configurations.
Exactly. The fundamental stable building blocks of reality in this theory. And then we have lambda alpha. These are the coherence eigenvalues.
Eigenvalues, like the energy levels in quantum mechanics.
Precisely. They are quantized measures of coherence reduction that correspond to resonance thresholds across fractal dimensions. Quantized means they can only take specific, discrete values.
So this is where the quantum nature emerges naturally from the geometry, not put in by hand.
That's the claim. These eigenvalues tell us about the specific, stable amounts of coherence that can exist, and crucially, how stable a particular coherent state is across different dimensions. It's the quantization of coherence stability.
So solving this whole thing is an eigenvalue problem at its core, finding the specific stable states L's and their corresponding stability values, lambda alpha.
Precisely. A well-established mathematical approach to find the stable configurations and fundamental modes of a complex system applied here to the very fabric of reality.
You mentioned the curvature term math alpha. How is that derived? Does it also involve fractional derivatives?
Yes, it does. To get the scalar math alpha, you first need the fractional Finsler curvature tensor. Lillian extends the standard Finsler curvature tensor to this fractional regime. The formula is quite involved. Rath alpha quant the Thormanchact May.
Alpha? Math alpha.
Okay, that's dense. What are the key conceptual takeaways from that formula? I see the fractional derivative alpha in there again.
Yes. The Gamma terms are the Finsler connection coefficients analogous to Christoffel symbols in GR, but for Finsler geometry, so they inherently know about directionality. And yes, the fractional derivative math acts on them.
So the curvature itself depends on alpha, on which fractal layer you're probing.
That is absolutely pivotal. The first key insight. Coherence curvature now depends on fractional differential order,
Well,
alpha. The bending of this phase space is directly linked to the fractal dimension and the coherence state. Its curvature changes based on how you look at it with alpha.
wow. Okay. And the second insight, stemming from that. For each alpha, a different curvature phase mode emerges, forming the basis of the eigenstate spectrum. This is where the magic starts. Each specific value of alpha yields a distinct mode of how coherence is structured by the curvature.
And these modes,
Uh-huh.
you're saying they relate to forces.
Lillian proposes these are the eigenmodes of the Finsler curvature tensor, representing phase-structured coherent states, directly mapping onto observable forces. The geometry itself, through these modes, is giving us the forces.
How do you actually find these solutions the eigenstates face? Is there a standard method?
Yes, it involves a variational principle, a standard technique in physics. You look for stationary solutions, states where small changes don't alter the overall configuration, indicating stability. It's expressed mathematically as minimizing an integral. Delta int, left alpha helm, plus math alpha inasat, plus math gal alt.
Looking for the universe's most stable, resonant frequencies, essentially.
That's a good way to put it. Finding the configurations that are most comfortable or energetically favorable for coherence within FCHP.
And what are the results? What do these solutions, the top assumptions and lambda alpha eigenvalues, actually mean physically? This is where the abstract math needs to connect back.
The results are profound. The eigenfunctions, the tapered solutions, correspond to coherence attractors.
Attractors, like stable states the system naturally settles into.
Exactly. Think of a complex ecosystem settling into stable repeating patterns. These tapest functions represent the preferred, energetically stable configurations that the underlying coherence naturally organizes itself into within FCHP. They are the fundamental, stable patterns from which observable reality emerges.
And the eigenvalues, lambda alpha, what do they quantify?
They quantify stability thresholds for coherence across hyperfractal layers. They tell us precisely how stable a particular coherence pattern is across different dimensions, indexed by alpha. They represent the quantized costs or energy levels of maintaining that pattern.
Okay, stability levels. And the final connection to physics.
This leads to the ultimate conceptual integration. Each solution defines a phase-selected resonance pathway, exactly what later appears as a gauge field phase.
So the mathematical solutions, these coherence eigenstates, are the direct precursors, the geometric underpinnings of the fundamental forces, the gauge fields.
That is precisely the claim. The mathematical harmony emerging from the FCHP directly dictates the very nature of the forces governing interactions in our world. The solutions are the proto-forces.
This feels like the climax, the grand reveal. If these coherent eigenstates are the precursors, how exactly do they map onto the familiar forces we know? Electromagnetism, the weak force, the strong force, this emergence of gauge symmetry phases. How does abstract math become concrete reality here?
This is indeed the remarkable result Lillian presents, and it fundamentally challenges how we've typically thought about these symmetries and forces. He shows that the discrete eigenmodes map directly onto the appearance of familiar gauge structures.
So the symmetries we observe in nature, the U1 of electromagnetism, SU2 of the weak force, SU3 of the strong force, they aren't put in by hand.
Exactly. Lillian argues that gauge symmetries are not imposed. They emerge naturally from the coherence eigenmode spectrum. This is a colossal shift. They aren't arbitrary rules. They are the natural consequence of coherence organizing itself into stable patterns.
Okay, let's break down this cosmic Rosetta Stone. What does eigenmode index 1, corresponding to the first eigenvalue lambda nullar, the most fundamental, stable coherent state, map to?
Eigenmode index 1 maps directly to the U1 emergent symmetry, and this physically appears as electromagnetic coherence.
Electromagnetism. Okay, and why does that make sense in this framework?
Because, as Lillian puts it, low-order lambda alpha correspond to high coherence phases. High coherence phases are very stable, very fundamental patterns, requiring minimal coherence reduction to exist. Think of a perfectly smooth, unhindered wave propagating infinitely.
And electromagnetism is a long-range force.
Exactly. These stable, high-coherence states manifest as long-range forces. Electromagnetism acts over vast distances. It's exceptionally stable. It governs light, electricity, holds atoms together. Its infinite range aligns perfectly with its emergence from a high-coherence, low-eigenvalue state, a foundational, highly stable resonance pathway of coherence.
So the theory provides a geometric, emergent explanation for why electromagnetism is long-range and stable. It's the ground state tune of coherence, so to speak.
You could say that. Now, what about eigenmode index 2, lambda 2, 2?
What force emerges from the next coherence state? Following the pattern, maybe the weak force.
Correct. For eigenmode index 2, lambda 2, we see the SU2 emergent symmetry. This physically appears as the weak force isospin phase.
And the logic here.
In stark contrast to electromagnetism, higher order lambda alpha correspond to deep coherence reductions. These represent less stable, more localized coherence states. They require more coherence reduction or energy to maintain.
And the weak force is very short range.
Incredibly short-ranged, yes, affecting particles only over tiny distances, like 11,000th the size of a proton. It governs radioactive beta decay, for example. Think of it like a ripple in a pond that dissipates incredibly quickly. Its coherence is profound, but very fleeting and localized.
So the framework links the instability or higher coherence reduction value lambda 2 to the limited range of the weak force. That's elegant.
It provides a reason why it's short range, rooted in the coherence stability.
Okay, so following this pattern, eigenmode index 3, lambda 3, should be the strong force, the one holding nuclei together.
Exactly. Eigenmode index 3 corresponds to the SU3 emergent symmetry, which physically appears as strong chromodynamic coherence.
The most powerful force, but also very short range, confined within protons and neutrons.
Yes. It binds quarks together, holds the nucleus together against electromagnetic repulsion. Like the weak force, its short range and its emergence from a higher order eigenvalue lambda 3 aligns with its highly localized and energetically intense nature. The strength and confinement are naturally explained by its specific coherence reduction value.
This is truly incredible if it holds up. It's like the universe tunes into different quantized resonance frequencies, different stability thresholds of coherence, lambda 2, lambda 3, and those frequencies manifest as the fundamental forces with their specific properties like range and strength.
That's the picture Lillian paints, a universe governed by coherence resonance.
But what about beyond lambda 3? Does the FCHP manifold predict anything else? Are there potentially unseen forces or phenomena lurking in higher eigenmodes?
This is where the framework becomes truly predictive and pushes beyond the known standard model. Lillian refers to hyperfractal higher-order phases, representing unmeasured coherence phenomena.
So, new physics.
Potentially. The FCHP manifold isn't just redriving known physics. It actively predicts hidden coherence phases beyond the three forces we currently understand. These could be linked to phenomena we're still trying to grasp or haven't even detected yet.
Like what? Any examples?
He suggests possible connections to things like neutrino oscillation damping. Neutrinos change flavors as they travel, and there are some puzzling aspects to how this happens.
Maybe interactions with these higher-order coherence phases affect them.
That's the suggestion. Perhaps subtle interactions, leakage between coherence layers influencing neutrino behavior. He also hints at dark matter condensates.
Dark matter, that's one of the biggest mysteries. How would this relate?
It's immensely intriguing. Instead of some exotic particle we haven't found, maybe dark matter is a manifestation of these higher-order, unobserved coherence phases, forming stable condensates due to their unique coherence properties. That would be a profound reinterpretation.
A coherence phenomenon, not a particle. Wow. Anything else?
And crucially, it predicts unmeasured higher dimensional gauge phenomena. As we probe deeper into the hyperfractal layers, tuning that alpha dial, the theory suggests entirely new forces or interactions linked to these higher emergent dimensions might become apparent.
Where would we look for those?
Maybe at extremely high energies, perhaps in early universe cosmology or in next-generation particle accelerators. It gives us new targets for discovery beyond the standard model.
So recapping this section, these coherence eigenvalues, the lambda alphas, aren't just abstract numbers. They directly quantify the stability thresholds for coherence across different dimensions and, in turn, directly determine fundamental characteristics of the emergent forces, their symmetry groups, U1, SU2, SU3, and properties like range and strength.
Exactly. It's presented as a remarkably elegant, self-consistent system where the rules emerge from the underlying structure, not imposed upon it. A statement about the fundamental nature of reality itself.
Okay, so we've journeyed through the FCHP space, the fractal calculus, the emergence of forces from coherence eigenstates. Now let's zoom out to the grand vision. The Unified Coherence Theory of Everything, or UCTE. How does FCHP, this whole framework, truly offer a path to integrate everything, quantum mechanics, relativity, forces into one single cohesive picture?
Well, FCHP is presented as offering a unified route to integrate quantum mechanics, relativity, and gauge field theory within the larger ontology of the Unified Coherence Theory of Everything, UCTE.
The grand ambition.
Absolutely. To provide a single framework where these previously disparate areas aren't just patched together or approximated, but genuinely derived from a common geometric source, the dynamic geometry of coherence itself.
A vision where the quantum realm, the macroscopic universe, and the forces governing them all spring from the same fundamental wellspring of coherence.
That's the goal. It's about finding that single source from which everything flows.
And this really hammers home that bottom-up versus top-down distinction we talked about at the start, doesn't it?
It does. Lillian reinforces why his bottom-up derivation of physics from coherence first principles is fundamentally distinct from, and he argues, superior to, top-down frameworks like string theory or conventional QFT.
Because those rely on imposed constraints.
Exactly. Things like compactified dimensions, arbitrary gauge sets, or probabilistic wave function assumptions. They start by putting certain features into the theory by hand, because we observe them or need them mathematically.
Whereas the elegance claimed here is that everything, dimensionality, forces, fields, spacetime itself, emerges naturally and dynamically from the fundamental geometry and coherence.
Yes, nothing needs to be put in as an initial assumption beyond the foundational principles of coherence within FCHP. It aims to be a self-organizing universe described mathematically.
So what are the key predictions or maybe the most far-reaching implications of this UCTE? Does it offer specific, testable hypotheses beyond the general idea of looking for higher-order effects?
It offers both conceptual reinterpretations and potential observational avenues. One of the most intriguing foundational insights is what Lillian terms hypergravity invariance.
Hypergravity invariance. What's that?
He describes it as the foundational coherence symmetry underlying space-time structure, of which gravity is an emergent manifestation.
Whoa, so gravity itself isn't fundamental. It's emergent from this deeper coherence symmetry.
That's the radical idea. Gravity isn't a separate fundamental force mediated by gravitons, perhaps. Instead, it's an emergent aspect of this more fundamental hypergravity invariant symmetry, intrinsically tied to the underlying coherence of spacetime itself within FCHP.
So the curvature of spacetime we experience as gravity is just a large-scale manifestation of how coherence organizes and flows within this multi-layered structure.
That's the implication. Gravity becomes a property of the coherence field, not a separate entity.
That would be revolutionary. What else?
Beyond that, the framework predicts a spectrum of hyperfractal dimensional unfolding. This isn't just theoretical. It means that as we probe different energy scales or look at different cosmological epochs, we might actually see the universe revealing more or fewer effective dimensions, depending on the coherent state and that alpha parameter.
Which leads to potentially observable effects.
Yes, directly to observable coherence effects in high energy and cosmological regimes. What might these look like? Subtle, unexpected deviations in particle accelerator experiments, tiny anomalies hinting at these hidden dimensions or coherence influences.
Or maybe explaining mysteries in the very early universe.
Exactly. Phenomena related to the Big Bang, inflation, maybe even dark energy. They can only be understood through this dynamic dimensional emergence and unique coherence interactions. It opens entirely new windows for both theoretical modeling and experimental searches.
So Lillian's work really presents a radical reinterpretation. Using Finsler geometry, fractal calculus, in this hyperfractal phase space, it creates a framework where reality structure emerges dynamically from quantized, coherence eigenstates.
It's holistic, aiming for self-consistency, where everything is connected not by arbitrary rules, but by the inherent patterns of coherence, a truly monumental conceptual leap.
A bold attempt to provide a mathematical framework where forces, dimensions, everything emerges dynamically and naturally.
The coherence-first approach, aiming to unify physics under a single, elegant geometric principle, potentially paving the way for that unified coherence theory of everything. A true symphony of physics, as you said earlier. Hashtag take that outro.
Wow, what an incredible journey we've taken today, from the profound idea of coherence as the very foundation of reality.
Through the intricate mathematical structure of FCHP and the very unusual tools of fractal calculus.
We've arrived at this stunning revelation, or proposal at least, of how familiar forces and even dimensions could simply be emergent phenomena from these elegant, quantized eigenvalue solutions.
It really challenges our most fundamental intuitions about the universe, doesn't it?
Absolutely. This Tier 4 Eureka breakthrough, as Lillian describes it, if it holds, truly represents a fundamental redefinition of how we understand dimensionality, field quantization, and ultimately how observable physics manifests itself.
It's not just a new theory. It's potentially a whole new lens through which to view the universe, inviting us to see interconnected patterns where we once saw separate components.
So what does this all mean for you, the listener? If gravity, electromagnetism, all the forces aren't just arbitrary laws, but instead are different tunes, different resonant frequencies played by the universe's underlying coherence, well, what other hidden harmonies might be waiting for us to discover?
And how might this coherence first view change the way we think about everything, from the smallest subatomic particles to the grandest structures of the cosmos?
It certainly gives us a profound amount to ponder, challenging us to look beyond the surface of reality.
It does. It invites us to consider that the deepest secrets might be found not in arbitrary rules, but in the elegant, self-organizing, emergent patterns of fundamental coherence. The universe as a coherent system in perpetual resonance.
A truly profound thought to end on. If you're feeling brave and your curiosity has been sufficiently piqued, we absolutely encourage you to look up Philip Lillian's original paper, Coherence Eigenstates, Fractal Calculus and Gauge Emergence. It's a deep dive in itself.
Definitely not light reading, but fascinating.
Thank you for joining us on the deep dive. We'll see you next time.